Good day, everyone. My name is Saeed. I'm a PhD student at LTU. My research focus on the edge architecture, but today I'm gonna mainly talk about 5G architecture. So basically, 5G to deliver service at edge. Basically, what we have so much hope to deliver of the service by help of the 5G. Let's just go. Okay. Mainly, I'm gonna talk about three different parts. At first, I'm gonna talk about why we need edge at edge, why we need services at edge basically, and then how 5G gonna help us to deliver those services, and how we can integrate edge computing in 5G architecture. So why we need services at edge? So this is very simple architecture of today communication. We have the user equipment, cell phones at the right side, and then we have a core network, either it could be 4G, 3G, 2G, or whatever, right? We have RAN also in middle. So to this point, seems everything is fine, but the vision that we are going to have a connected society, it means that we have gonna have a huge number of IoT devices or objects communicate to each other. With reference to 3GPP release 16, the basic requirements is the 5G basically has to deal with 1 million devices per square kilometers. So that's gonna put a lots of emphasis on the infrastructure, mainly on the backhaul congestion. So all these traffics has to go through all the core network and come back. And then let's not forget that we have a demanding always at the right side of the user equipment. So we are talking about the millions of connections if you want to achieve the connected society. So one of the obvious solution, bring that computing on the center closer to the edge. We call it edge servers, or as Etsy call it, multi-access edge computing. So in this regards, we can offload the computing at the edge sites. And then we have a break the traffic, and then we have a basically some processes happens on the edge and the others happens on the core network. With the same fashion, we can also put the caching here. Another aspect of the future traffics is expected that streaming video is expected that the streaming video is actually the highest traffic in the future. So with the same fashion, we can put content here, and then we can relieve the traffic from the backhaul. So two of the significant result of this architecture is latency and speed, because now the process and majority of the communication happens close to the users, so we can have speed and latency. And just let's not forget that, for example, when we are talking about the IoT, we are talking about the critical IoT, we are talking about autonomous car and grid networks, infrastructure in the smart city, and many things that the latency is very important. So now we distribute the edge in a different edge sites. We have a problem now how we can orchestrate and manage all these distributed edge servers. Mainly we are talking about, let's say, lifecycle management, how we can go about discovery, modification, deletion, and creation on the lifecycle management, how we can scale up and down and make them available and make them resilient in when we have a failure in the system. Security is a very important part also in this architecture, because now we have a distributed sites that we cannot have the solid security perspective in one site. It's distributed, we have a wider surface attack. So that's also another important part. We're talking about the maintenance. We very much like to have a zero-touch maintenance and basically automation, again, because we have a very distributed architecture. These are some of the challenges. We have also, let's say, quality of experience. We are talking about the Zigbee, Bluetooth, Wi-Fi, wired, 3G, 2G, 4G. There are so many diverse network infrastructures. How we can deliver the same quality despite the infrastructure. So let's just talk about the 5G itself, how 5G designed to deliver some of those challenges or hopefully solve all of them. So to this point, this is basically the cellular history, kind of. Like to this point, we basically have these kind of problems of the scalability, latency, again, talking about the different diverse infrastructures and a slow connection. So in the 5G, we are aimed to deliver the ultra reliable low latency. In 5G, we have different architecture at the heart of the 5G. We're going to talk about the service-based architecture, COPS and virtualization. The fruit of this architecture, network slicing and cloud run. Just small point here, the 5G, based on the specifications, should deliver 10 gigabytes download and 20 gigabytes upload. It's very fast compared to the earlier generation. Moving on the service-based architecture. So this diagram basically compared from the 2G to the 5G. My focus in this packet data network, specifically on the 5G core here. As you notice that we have network function 1, network function 2, and n. This is actually the service-based architecture in the 5G core. We can dynamically create different functions depends on our need. These are virtualized. If you compare to the earlier generation, they are basically dedicated hardware. Let's open up on the, so this is a bigger picture of that service-based architecture. All these elements, as you can see, majority of them could be virtualized. We have, for example, network slice selection function. We have network repository functions. We have access mobility management function and session management. These are actually AMF, and SMF represents MME in the earlier generation. We have user plane functions and many of them. So at any point of time, we can create define a new functions and use it in the architecture. More or less, we can basically select those dedicated hardware, use the commercial off-the-shelf servers, and virtualize it. In this diagram, we call it mono. Actually, if you are interested in this topic on the Etsy, this version is talk about the details of this architecture. But we have virtualized elements of those core network here, and this is the hardware. So we have an orchestration that's based on the communication, based on the needs, we can scale up and down for any elements. Some of the benefits of this could be resource orchestration, for example, and network service management. Another new aspects in the 5G is COPS, control user plane separation. This is also very significant in the 5G. For example, in the user plane functions, this is pretty much deal with a serving gateway and proxy gateway in 4G, a evolved packet controller. Or in the control plane, we are dealing with the authentication server functions, for example, session management functions, policy, and also like some other elements that's dealing with the control plane function. But how COPS can help to reduce the network traffic. So remember that the COPS, we are basically separate the user and control plane. So we have a loosely coupled. So with that regards, we can put the control plane, let's say, with the user plane in the same place as the way they have it, like a data center. We can distribute both of them, the control plane and user plane distributed completely. Could be on the Cloud Run, for example. Or could be the control plane centralized and we have multiple user plane on a different location. So we can just go about different deployment based on our architecture and needs. To just give you an example here, for example, just imagine that in the college, thousands of the students streaming video games. So in that regards, we need more user plane. But in contrast, if you consider the shopping mall with thousands of mobile users, then we need more control plane to deal with the session of each user separately. As a result of this architecture, also we have session and service continuity. We have different types of continuity in this 5G. The first one is basically is a traditional one. We have a we're gonna move to the new location without losing the anchor. So we have a stable connection. In the second one, break before make, we're gonna break our PDU session and create a new one, and then create a new anchor point. At this point, either we're gonna use the same IP address or not. It really depends on the architecture on the core network and the mobile network operator. Make before break, before we are moving, we're basically gonna create a new connection, then we move. We're gonna have a stable connection in this regards, but definitely we're gonna lose the IP address. And the other benefits of this approach is that we can give a unique user plane function to the users with regards to the new condition that we have on that aspect. In the QoS also change in the 5G because again, we have user plane and control plane separately. So for example, in this is one thing that I have to mention here, that when you are creating when the user communicate in the network, they are gonna create the PDU session. So in that PDU session, by default, we have one QoS flow comes by default. But of course, the mobile network operators, they can customize it and create multiple flow ID, just like this diagram here. We can even get the service data flow template and modify it and customize it in different environment and requirements. On the 5G, QoS can be done on the core network by using one or more PDU session, or could be on the next generation RAN by one or more data radial barrier per PDU session, for example. This is also gives us the capability for the edge computing. We can customize more granular the traffic, basically. Of course, after all this architecture, some of the network slicing has become very obvious. So whether we need mobility, we can just dedicate those kind of resources. If we are dealing with the massive IoT, again, we have a different types of resources. It goes for the speed and latency as well. So how we can embedded 5G, how we can embedded edge platform in this 5G architecture. So where you put the edge is really depends on your requirements. So for example, here I have three different category of the edge. For example, if you put it on the data centers, you're going to deliver 20 to 50 milliseconds latency. The number of sites could be less than 40. When we are going on the virtual LAN, the breakout here, going to be 5 to 20 milliseconds. And the number of servers going to be 10 to 80, for example, or it's going to be at the radio, at the base station, very close to the edge. They call it deep edge on the white paper. So we're going to have a delivery of 1 to 5 milliseconds. So this is the software service-based architecture on the 5G. So based on the ETSI requirement specification on white paper, the multi-access edge computing or edge architecture basically can have two components, main components. One of them is a distributed one at the bottom one here, which is going to communicate to the user plane function. And we have orchestrator to basically manage all this distributed host edge component. Moving on, so this is a bigger picture of the earlier slide. So when we have an orchestrator and when we have a distributed edge host, we can deliver basically expose three different aspects of our orchestration. We can monitor user equipment roaming status. We can check whether we lose the connectivity or not. We can check whether we have a user has a reachability or not. Some of the elements on the monitoring could be AMF, or access mobility management functions, session management functions, and UDM, for example. We go for the provisioning. So what if your user move for another from one point to another point? So we can predict user equipment movements and provide provision this, for example, services. And of course, we can deal with the policy and charging. So it depends on the user request whether we can allow or not allow. This is also very generic to just show you how edge mobility gonna work on the edge based on the 5G networks. You notice that our request is go all the way from RAN to the user plane functions, and then the other aspect is basically abstracted from the communication. Because again, because our traffic from the user is gonna go from the PDU session, is basically a kind of tunnel. And lastly, this is some of the example how you can deploy the edge architecture. So in the first diagram here, you can put the edge and user plane functions at the base station. You have it up top here and down here. This is the very closest to the user equipment. In the second approach, you can put it on the collocated with the transmission node. Possibly you could have a local user plane function. In the third option, you can put it on the network aggregation points a bit further from the base station. And finally, in the fourth steps, you can put the edge computing in the core network. Kind of is more or less the same as the cloud that we have. Okay, that's for me. Thank you so much.